Hello, Gen Chem students. I wanted to go over percent ionization in a little more detail because it showed up on a lot of your mud cards today, and I wanted to make sure that we were all on the same page. So to begin with, percent ionization expresses how much of an acid or base dissociates into ions when it's dissolved in water. This occurs through the acid or base reacting with water to produce hydronium or hydroxide and the conjugate acid or base. Let's take a look at a sample exercise here. Let's say that we have a sample pool of 100 acid molecules. Since this is currently the pure acid, none of it is going to dissociate. There's no water around for it to react with. If, however, we drop this acid into some water and let it dissolve, then some portion of this 100 molecules is going to dissociate. In this case, we have 90 acid molecules that do not dissociate, but we have 10 that do, and they dissociate into the hydronium, H3O plus ions, and 10 conjugate base ions. Now we've got 10 of our acid molecules that dissociated out of a pool of 100. 10 out of 100 is 10%. So we would say that this acid is 10% ionized in water. And we can use this as a more general equation as follows. For acids, the percent ionization will be the equilibrium concentration of the hydronium over the initial concentration of the acid times 100%. For bases, you focus on the hydroxide. You want the equilibrium hydroxide concentration over the initial base times 100%. Both of these expressions are simply telling you what percentage of the original population of acid or base has dissociated now that it's gone into water. Let's take a look at an example problem. Here's our example. Hydrofluoric acid has a percent ionization of 8.5% at a concentration of 0.1 molar. We want to find the hydronium concentration at equilibrium, the pH, and then the K sub A. The H3O plus concentration we can find from the percent ionization, and then we can use this concentration to get us to both the pH and the K sub A. We're going to start by taking a look at the chemical equation for this process. HF will react with the H2O to make fluoride ion and H3O plus ion. We're going to look at our mass action expression. K sub A equals the concentration of hydronium times the concentration of fluoride over the concentration of HF. And remember, we leave the water out of this because liquids and solids never show up in mass action expressions. What we're going to do is use that percent ionization to calculate for the concentration of H3O+, and then we can use that to solve for the equilibrium concentrations of these other two components. And like any other equilibrium process, we can just plug in the equilibrium concentrations to the mass action expression to solve for its equilibrium constant. Well, let's get cracking. The equilibrium concentration of hydronium, H3O+, will be equal to the original concentration of the acid times the decimal form of the percent ionization. We do this because the initial concentration of the acid is the amount of acid available to dissociate. This is like that pool of 100 acid molecules we saw on the previous slide. This second term, this tells us the portion of that acid that actually dissociates, and therefore gives us the concentration of that hydronium. Let's take a look at it with the numbers. The H3O plus equilibrium concentration equals 8.5% ionization divided by 100 times 0.1. That's the original molarity. That equals 8.5 times 10 to the minus third molar. Now note, 8.5 times 10 to the minus third is 8.5% of 0.1. That's what this means. Now we can take this equilibrium molarity of hydronium and use it to calculate pH. All of you are, I'm sure, very familiar with this process by now. You just take the negative log of that hydronium concentration, so negative log of 8.5 times 10 to the minus third, and you get your pH, 2.07. So now that we have the equilibrium concentration of H3O+, we have all we need to get started on solving for K sub A. Let's take a look at how. To get at each of these equilibrium concentrations, we'll first take a note. So we have H3O+ concentration. We need fluoride. The fluoride concentration will be equal to the H3O+ concentration because there's a 1-to-1 ratio of these two species in the chemical equation. Therefore, the concentration of both H3O+ and F- will be 8.5 times 10 to the minus third molar. To get at the equilibrium HF concentration, we need to take a look at the relationship between the initial and equilibrium concentrations represented by the percent ionization relationship. We can say that the initial concentration of HF minus the equilibrium concentration of H3O+ should equal that equilibrium concentration. Now that's because the H3O+ comes out of that initial pool of HF. It reduces the amount of HF there. So if we remove the amount of H3O+, what we have left will be the equilibrium HF. We plug this in, 0.1 minus 0.008. We get that the equilibrium concentration of HF is 0.092 molar. Now that we have the equilibrium concentrations of all our components, we just plug them into the mass action expression. K sub A will equal 8.5 times 10 to the minus third squared over 0.092. Crunch that down and you get 7.8 times 10 to the minus fourth is our Ka. So I hope this cleared things up. I will see you guys on Friday, and good luck on your 15B Smart work.